Okay, so today we're going to continue with the second section of this unit, looking at what are called net ionic equations. Okay, so we've talked about solubility and how some things can be aqueous, which means they would dissolve in water and we would put an AQ. And then we also talked about things that are not aqueous in water or form precipitates, which we call solids, and so when we're doing physical states, we would put an S after them. So there are basically three ways to write reactions, and the first one you should be really familiar with. We've done this one before. It's called the molecular equation. This is basically just your balanced chemical equation, all the reactants and products, and the physical states. Okay, the second and third ones are going to be new. So the second one is called a complete ionic equation. It's complete because it represents all the electrolytes for all the compounds in the entire reaction. So if something is aqueous, which means it breaks apart, it breaks into its ions in water, then instead of showing it together as a compound, we're going to show it as separate ions. And so this better represents what's really going on in a beaker with two compounds, or in a reaction. Okay, but this can get a little messy because we have a lot of these ions all floating around. Some of them contribute to producing the product, some of them don't. They're called spectator ions. And so we also have a third type, which is called a net ionic equation. And this includes only compounds that are involved directly in producing whatever product we're interested in. Okay, and so we'll talk some more about that, but these are basically your main three types. Okay, so let's talk a little bit more about each type. So first of all, here's an example of a molecular equation. So we have potassium chromate, and it's aqueous, which means it's actually existing as ions, not as one solid reactant. And then we have barium nitrate, and it's also aqueous, because if you remember from your solubility rules, anything with nitrate is always going to be soluble or aqueous. Okay, and then we switch the partners on both of these. So we have our positive potassium. We put it with our negative nitrate, and then we also put our positive barium with the negative chromate. And so we form two products. So barium chromate, if we look at our solubility rules, ends up being a solid or insoluble. And then remember, anything with nitrate is aqueous, so we have our potassium nitrate. So this is the regular type of equation. We've got our products. We've put all the physical states, and we've also balanced everything. Okay, so this is nothing new. But now we're going to start representing how the reaction actually occurs, how those products and reactants actually exist in a beaker. Okay, so if we look at our complete ionic equation, we know that we have to take everything that's aqueous and break it up into its ions. So let's take this first compound, potassium chromate. We know that we put the 2 here on the potassium because chromate is a 2- and potassium is a 1+, and so in order to make that neutral, we need 2 potassiums. Well, that means that because it's aqueous and breaking apart, that there are 2 potassiums floating around. And so we're going to write that as 2 potassium ions, and that's why we put the 2 out front, and that's also why we put the charge on it, because now it's an ion. And then we're also going to put our chromate ion, but we only have one of those. Remember, CrO4 is one of our polyatomics, so it's 1 unit, and that is a 2-. Okay, now let's go to the barium nitrate. Well, it is also aqueous, which means it's going to break apart into its cation and its anion. Okay, well, in this case, our cation is the barium. So remember, cations are positively charged. And then this 2 outside the parentheses means that we had 2 nitrates. So remember, we want more than one polyatomic, we use parentheses. So we have 2 NO3 1-. Okay, that takes us to the product side. So we'll put our arrow just like we've got on the molecular equation. Now we get to our barium chromate. Well, barium chromate is a solid. So it is going to stay together. That's our precipitate. That's the product. And so that's not going to break apart. It's not aqueous. And so we'll write the whole thing and put the physical state. And now we get to a potassium nitrate. Well, that's aqueous, which means it's going to break apart. And this 2 out front, remember, applies to everything in that compound. And so we have 2 potassium ions and 2 nitrate ions. So it's still the same equation. Everything is still balanced. We're just now representing what's exactly going on in that beaker when we mix potassium chromate and barium nitrate together. Okay, so the third step is the net ionic equation. I don't know what that thing is. There we go. Okay, and in the net ionic equation, now net ionic is different from complete ionic because net is kind of like, you know, canceling out all the extra stuff. It's the sum or the net. Okay, and so we cancel out everything that occurs on both the reactant and product side of the equation. It has to be identical on both sides, and these are called spectator ions. So they're not really playing the game, they're just spectating. So they're not contributing to the outcome, they're just kind of there. Okay, so if we go back up into the complete, and let me get a different color. Okay, so if we go back up into the complete ionic equation, see if you can see anything that's exactly the same on both sides of the reaction. Okay, and hopefully what you've identified is that we have 2 potassium ions on the reactant side and 2 on the product side. So we're just going to draw a line through those. Those would be spectator ions. Nothing really happened to them when they went from reactant to product. They just stayed as 2 potassium ions on the reactant side, and then nothing really happened to them. Okay, hopefully the other one that you've noticed are these 2 nitrate ions. So these will cancel and these will cancel. Again, they're identical on both sides of the reaction. That's really key. The reason we can't cancel out the barium or the chromate is because here they're stuck together. Remember, this was a solid, so we couldn't break it apart. It's not aqueous. And so they are not identical. Even though we have the same species, on the reactant side they're by themselves, and on the product side they're together. So we can't cancel those out. So basically, once you have canceled out your spectator ions, now you write down what's left. So we have our chromate and our barium ion, and that produces a precipitate or a solid of barium chromate. So something that you kind of want to notice, this is why it's really important to balance the equation, because we have a balanced chemical equation as our last step. We were also able to cancel out identical quantities of our spectator ions. If I hadn't balanced this equation and I had 1 potassium nitrate over here, then it wouldn't cancel equally, and that should kind of tell you that maybe you didn't balance or there was some sort of issue. So your end equation, your net ionic, as well as your complete ionic and molecular, they should all be balanced all the time. Okay, so let's try a few more examples. Okay, so we want to write each of the 3 types for this reaction. So we have aqueous sodium chloride. So I know sodium chloride is NaCl. We have a 1 plus and a 1 minus, and it's aqueous. And it's added to aqueous silver 1 nitrate. So silver, and this Roman numeral 1 tells me it's a 1 plus. And nitrate is NO3, and that's a 1 minus, and it says that it's aqueous. To form, so I know I want to draw my arrow, solid silver 1 chloride. So silver, again, this Roman numeral tells me it's a 1 plus. Chlorine I know is a 1 minus, but this time it's a solid. Plus aqueous sodium nitrate. Sodium is a 1 plus. Nitrate is a 1 minus, and it's aqueous. So something that I always do when I'm writing the molecular equation is put all the charges for all the ions. So 1 plus for the sodium, 1 minus for the chlorine. It does 2 things. It helps me make sure I write all my compounds correctly, because that is really important to start off with. If you need, let's say you had, like aluminum chloride. This is not neutral the way that it's written. I would need 3 chlorines in order to make that neutral. So all those, the naming and the nomenclature and the writing the compounds the correct way, all that stuff still matters in this. Okay, but we got really lucky. Everything was +1, -1. So everything should be written correctly, and because everything is 1 to 1, this also should be balanced already. Okay, so our molecular, we're all set. So here's our molecular. Okay, now we want to go to the complete ionic. So we're going to take everything that's aqueous and break it apart into its ions. Okay, well, sodium chloride's aqueous, so I know I have 1 sodium ion and 1 chlorine ion. When you're writing ions, it's really important to put the charges. That distinguishes an ion from a neutral atom. Okay, so now we have silver nitrate. So we have a silver ion, and this is also aqueous, and the nitrate. Okay, so now we get to silver chloride. Well, that is insoluble, or it's a precipitate or a solid. So we're just going to write silver chloride and keep it together. And then we have our sodium nitrate, which is aqueous. And so we can break that apart. Okay, and that's our complete ionic. We've broken apart everything that's aqueous, and we've kept things that are not aqueous, or things that are solid, together. Okay, now we want to write our net ionic. So now we're going to look for things that are absolutely identical on both sides of the reaction. Let me get a different color pen. Oops, wrong button. Okay, so let's see. I see a sodium ion on both sides, and it's by itself, same quantity, so that can get canceled out. And I also see a nitrate ion on both sides. I can't cross off the chlorine or the silver because here it's together as a compound. And so I'm going to write down what I have left. So I have the chlorine ion plus the silver ion, and that produces silver 1 chloride, and it's a solid. You can list your ions in any order because as I broke them apart, chlorine was listed first. That's completely fine. You don't have to list the cation first and then the anion second because here they're just ions. It only matters when it's in a compound. Okay, so try this one. Now make sure that you write your compound correctly, check your charges. Well, maybe we'll write the compound together. So maybe pause it, try writing the molecular, and then go ahead and play the video again, and then we'll check, and then you can try the complete ionic and the net ionic on your own. So go ahead and pause and try this, and then I'll go through the answer. Okay, so we have aqueous potassium hydroxide. I know potassium is a 1+, hydroxide is a 1-, and it's aqueous. And it's mixed with aqueous iron 3. Now that means it's a 3+. Nitrate is a 1-, even though the 3 is here, this is an entire polyatomic. So parentheses and a 3, and it's aqueous. And that forms solid iron hydroxide. Well, hydroxide is a 1-, so I know I need 3 of those, and it says it's a solid. So that's our inaqueous. And then we can also have aqueous potassium nitrate. Potassium is a 1+, nitrate's a 1-. So that's all set, it's written correctly, and it's aqueous. So now the last thing we need to do is make sure it's balanced before we move on to the complete ionic. Let's see, I have 3 hydroxides, so I need a 3 out front here. That means I also have 3 potassium, so if I go over to the nitrate, I need the 3. That makes 3 nitrates, but if I look with my iron 3 nitrate, I've got 3. So now I'm all set and it's balanced. Okay, one thing that you might run into sometimes, what you've noticed is that hopefully, is both of our reactants are aqueous and only one of our products is aqueous and the other one is our solid, because this is our product of interest. Sometimes you will get all aqueous products, and what will happen is you'll write out your complete ionic and you'll write out all ions, but then everything is going to cancel for the net ionic. So in that case, we would just write NR for no reaction. So just keep in mind, almost always, one of your products will be a solid, but there is always that chance where you're not going to produce a precipitate and everything will be aqueous. And that's okay. If that happens, it's no reaction. Okay, so what I'd like you to do, this was our molecular. Try the complete ionic and the net ionic. Okay, and then we'll check answers when we discuss in class. Have a good day.